Good afternoon or evening, everybody. Hey. So welcome to Building Resilient Services, Learning Lessons from Azure. My name is Mark Russinovich. I'm the Chief Technology Officer of Azure. I've been in Azure for about 6 years now, so I've seen it come from just a little project running in a few different regions to being a hyperscale cloud running now in 30. It's been an incredible journey, and it's been a journey learned with lots of lessons, because as you know, when you start small and you start to get bigger, you start to run into problems that you didn't see before, and you start to have to come up with solutions in innovative ways to address problems that most developers never have to run into in the real world. Now, the fact is, though, that more and more, every company is becoming a cloud services company, a cloud application company. And every company needs to move quickly. Every company is updating software to meet new business requirements, rolling it out. And one of the requirements is being on 24/7 and rolling those updates when they go out in a reliable way. So I figured this session, I would share with you a whole bunch of learnings that we've gotten from Azure, from actually running our services in Azure, kind of learning them the painful way, running into incidents and saying, wait a minute, how do we prevent that class of problem from never happening again? And then kind of institutionalizing these learnings. So that's one of the things that we try to do, and I recommend you do within your organizations too, is whenever you have a learning in your own application, to share it with all your colleagues, because these are best practices that you don't want everybody to have to stumble on the same problems in the same way. Now, how many of you are developers? Just let me get a raise of hands. How many non-developers are in here? All right, I just wanted to make sure you were all awake. And I realize I got a problem, because this is really an IT pro-focused talk. So I think, let me switch the deck. No, I'm just kidding. This talk is actually aimed at developers. Now, how many of you resonate with this quote? Well, this is a quote that you should also look at and respect. And that's the point of this talk. Now, these first set of lessons, and again, all of these are from real production in Azure, I'm going to share with you are kind of mini lessons. They're ones where we've had little mini incidents, where we've had ones that didn't necessarily cause outages, but caused our developers pain. And I'm going to share some of the best practices that go with those with you as I go through these. And then what I'm going to do is proceed into some larger incidents, one where we did have outages, one where we did see some impact and where we went back and did a root cause analysis, which we do for every incident that we have, come up with the mitigations, short-term, long-term, and come up with, again, the best practices. So let's go ahead and start with one. And I figured since you're developers, you can look at this and see where the problem is in this line of code, which is from production code in one of our services. Anybody spot it? I'll give you a hint. That if statement, what does it evaluate to? Here's another hint. So this if statement actually consists of two expressions separated with a comma. The second one is true. So this if statement actually is if true. The problem with this is in a piece of code that gets called by the system whenever it determines if it should log something. So when this went out, it broke the logging system. It basically flooded the logs. And that actually, in one of the cases that you got to be careful with, is when logs fill up disks, and we've learned this lesson too, be careful to constrain your logs. Don't let it run amok on your production servers and take over all the disk space. So what we do is set quotas on the amount of log space that can be there. So if we've got a problem rolling over the log or dumping log files, that we don't end up impacting the production service by running out of space. But that's exactly what happened in this case, impacted the production service. And the lesson from this is when we went back and looked at how this got into the production code is that there were a whole bunch of warnings being suppressed in the build system. How many of you go and suppress warnings just as like, oh, forget it, I'll deal with that later. That's noise, suppress. So the lesson we learned was actually, if you're going to be running a production service, you need to look at every warning and treat it seriously. And do not suppress. Try to clean up everything you possibly can. So the rule here is don't suppress compiler warnings and don't ever compress. So one of the things that we see is people that turn on full warnings and then just go and suppress back to the point where they were, like warning level 3 or 4 in the end. So don't do that. Speaking of logs, one of the things you also learn is that when you're running a production service, it's a lot of times hard to reproduce a problem. So you need to log enough that when something happens, you can go look at the logs and root cause what happened. So when you're logging, you need to be thoughtful about what you log and think about, I'm not necessarily going to be the person looking at this log entry. Somebody else that's troubleshooting a problem is going to look at it, and is there enough information for them to actually make use of it and figure out what's going on? I want to share with you some of the log messages that we've had come out of our services that have caused the people that are doing the live site response major pain because they're somewhat incomplete. Here's one. So the problem with this one, obviously, is that end part. The service name is unknown. And the question that the responder has is, what service name? If I don't know the service name, I can't go figure out what's causing this problem. Here's another one. This is in a test environment where this was getting thrown into the logs. Something was failing, and the investigator goes and looks at the logs and says, the subscription is not authorized for this resource provider. What resource provider? Some resource providers, some subscription is calling some resource. It's not authorized for it. What is the resource, and more importantly, what is the subscription I need to go look at to understand what is screwed up in the test environment's configuration? So this kind of problem leads to several hours of trying to track things down. Here's another one. And this is probably the most problematic, because as you're going through and you're trying to figure out, is this a bug or not? Well, what is the versioning header? And I need to go look at it to understand what malformed request came from one of our other services into this service that I need to go and fix so that this doesn't happen. So that's a little bit look of logs. Now, one of the things that oftentimes generates records or entries on logs is when you have exceptions. And so we've learned some rules about exception handling. How many people wrestle with exception handling in your code? Just a few of you? Everybody else has got it figured out? All right. So one of the problems is that when you're dealing with exceptions, a lot of times you're dealing with code that you're calling and you have no idea what it's going to throw back at you. This is especially the case when you're importing third-party libraries. And you don't know, are they going to return an error for this? Or are they going to filter it all the way up the stack? Or are they just going to throw something up and say, I don't know what to do, and I've got to sit up here at the top and try to figure out what's happening? So one of the questions you've got to wrestle with is, when I get this exception thrown out from the code that's not an exception that I'm looking for out of my own code, what do I do with it? Should I catch all, or should I fail fast? Should I basically say, OK, I don't know what to do with it, I'm just going to ignore it? Or should I say, I don't know what to do with it, life is screwed up, I'm going to kill myself? What do you think the answer is? If you go look in Visual Studio documentation, what do you think the answer is? So this is the rule. Do not catch general exceptions. The problem when you're looking at this from a service perspective, though, is that on one hand, if you catch an unrecoverable error, you can have your service in a really screwed up state. And it's going to eventually fail in some other way, and what you've done is just basically suppress the root cause of the problem. Or, even worse, you put the system in a screwed up state and it's going to end up corrupting data someplace down the road. On the other hand, you fail fast, and you could end up causing a problem where users can DOS your system, because if the cause of the exception was some malformed input from some untrusted source, then what you've done is made it so that some untrusted source can bring down your service. So what we've realized, and this is code over here on the right from our storage service, is that we've got to be very careful with exceptions. And first of all, when we write our code, we don't throw exceptions for everything. We return for anything that is expected, a kind of expected error, we return it as a result and pass that up the function chain. Only for something that is catastrophic would we throw an exception, or really some unexpected situation. the service is in a screwed up state, I need to throw an exception because I don't know what to do with this, and if I pass it up, whatever code is getting this probably won't know how to handle it. So in the code here, we've got a final handler that is called for after all known exceptions, all expected ones are processed, and then this function is called, is crashing exception. And this function goes and looks and says, if it's not a user-initiated crash and is also not recoverable, then what we're going to do is log to a file and terminate ourselves. Otherwise, we log an error and return the error. Now, handling errors is something you got to pay attention to as well. This code path right here, which is where we're logging an error and then returning. So what happens if the user, the client code, is calling us, getting an error, and not dealing with it in the appropriate way? Because they don't expect that error, and so what does client code oftentimes do when it gets back an error that it doesn't expect? It tries again, it retries. And so it's going to sit there and retry, and then what's going to happen to our logs? They're going to get blown up with this error. So basically our logs get DOSed. So we've got also a rule, and this is something that we learned very early on in the storage system as well, as part of this code, is that that alert or log exception is looking at context around this exception, like what client has generated it, and only logging this once per hour, per exception, per machine. And we don't report HTTP 500 back to the caller either, because that will cause them to know that they can DOS our system. So that's a couple of rules around exceptions. There's some more rules that we've also learned around exceptions, and that is that exceptions are expensive, especially if you're going to log and try to capture a stack trace, because that's CPU intensive. And if you've got a server that's under load and starting to get exceptions, you might just end up pushing it over the edge. So one of the rules that we've got is that we, again, control how often we generate a stack trace based on some time interval so that we're not generating stack traces for every single exception and, again, allow ourselves to get DOSed. And sometimes, in cases where you've got code that's flowing through and can be generating exceptions all the time, maybe make it so that you can dynamically turn on the exception trace so that you're not doing it under normal circumstances. So that's another one of the rules that we came out with. Another rule is that with async kind of patterns, you have an exception that is thrown, but on the end method, now you've lost the context for that exception. And so one of the things that you sometimes see developers do is that they go and try to get the exception off the remote thread, and that causes that remote thread to freeze as the stack is walked, and the exception record is being generated for that end method to finally drop it into a log file. Do not do that, because you're going to kill the performance of your service. Instead, what we do is that we pass an exception record as the inner exception for the outer exception that's thrown by the end call, and that avoids the stack walk across threads. So if you're going to pass an exception out from an async method, this is the way that we've figured out how to do it. So here are some rules related to exceptions. Another rule that we've learned when it comes to logging, and sometimes logging in the face of exceptions, is to be careful about the way that we format our logs. Here's an example log. This is from production as well. And there's an interesting record in the log. So these are log record number 9, 15, and 22. And you can see number 15 is role 1db, d1db, web role instance 2 has current state unresponsive, desired state started, and goal state execution status updated succeeded. This is an error condition where this instance is unresponsive. And there's the timestamp for it. Now, one of the first things you do when you have a log like this is that you go look at your other logs from other systems to look for correlating information and more detail about what's happened. Something elsewhere in the system has possibly caused this to go unresponsive, because this is just reporting the state. Maybe something else knows what has moved this into the unresponsive state, and so we need to go searching through those other logs. And one of the things that you're going to do ideally is have correlation IDs across your events, but that's not always possible. So the next thing you do is go look for time windows to see if you can find the related events. Well, for this particular incident, here's the second log file that actually has the root cause for this, which is right there, state of D1 DB, web role instance 2 changed from role state started to role state unresponsive, and this is in the log file from the system that actually changed the state, which resulted in that other message. But if you look at the timestamp on this, you can see that it's a very different timestamp than the one above, and actually this caused the developers to spend roughly 45 minutes digging through logs by doing searches not for time, because they look at the time window, see nothing that is related to the first log. So they're looking for error messages that are related, might be related. Finally stumble across this and realize what? One system, yeah, time zone. How many people have run into time zone problems in your logging? So this is a painful, painful lesson. I can see a lot of you have already learned. So obviously here, one log was in Pacific time, the other one is in UTC. So what's the rule here? UTC. And if you're going to display something back to the user, of course, and they expect to see something in local time, that's when you do your transformation. But otherwise, internally in your systems, UTC everywhere. OK, here's another example of a rule that we've learned. So developer starts with a piece of code, a sample code. They get pick up from somewhere. So here's ASP.NET Web Apps sample storage. Now they want to hit F5, ready to go verify the app. Here's the code configuration. And there's this right in there that says, hey, you need to provide a storage account. So they fill it in. Do F5. Looks like the sample's working. Now let's share that sample with the world. And suddenly you've got your test account keys up in GitHub. Has anybody done this? You wouldn't admit it, right? So we've all heard stories about this happening, and it's very easy to happen. It's very easy to let it happen. If you're going to be putting your secrets into your code, baking it into your configuration, you're going to end up with this problem eventually. So one of the rules, and by the way, here's what happens when you post it. You're giving everybody free cloud storage. So the rule here, the root cause, of course, is that you're pushing keys, and thank goodness in this particular case, where we had something like this, it was a test account key related to this sample code. But worse, it could be production code. So one of the things that we've done is institutionalize keeping all secrets. So there's internal systems that we've got called Secret Store. That's where we put our secrets. There's only references to it by code, never actually secrets. So at the time of deployment, the secrets are fetched. And for higher level services and anything we do publicly in Azure, the answer is Key Vault. Put all the secrets in Key Vault. Azure Resource Manager has a flag that you can give access to the Key Vault, so when it's deploying your code, it can go and pull out the secrets and inject them as configuration at runtime as it's deploying your service, your application, and so your application never has to mess with the secrets directly, and you don't have to put them into your configuration. The other thing we've learned is that in some cases, you might have developers that are playing fast and loose and don't know the rules. And in this particular, in many cases, it's like, OK, let people learn the hard way. We'll go and figure it out later and tell them don't do that. And we'll educate and have boot camps and so on. But this is such a risky situation that we take the step of putting check-in gates that are scanning code, looking for places where credentials are sitting inside a configuration and blocking the check-in. We also, just in case something slips past then, have cred scanners that are marching through code continuously in our source repositories looking for this situation and then sending alerts when it finds them. So this is something that you should probably do too, because this could potentially be really catastrophic to your business if a secret gets leaked out. And we've seen cases in public where that's happened. So that's a few of the kind of just rules of the road kind of tips. What I'm going to share with you now are a few incidents. I've got 4 incidents to share with you, all highlighting different lessons that you can take away for creating your services and operating them. And these are all real. They're all from the last year and a half or so across a variety of our different services. This first one, and these, just to show you that they're real, here's a real incident page. This one, a whole bunch of websites basically went off that were being managed by Azure Traffic Manager, suddenly disappeared from the web. Not all of them that were being managed by Traffic Manager, just a subset. So let me walk you through what happened when this incident took place. And we have to start with the way that Traffic Manager, what is Traffic Manager and how does name resolution work with Traffic Manager? So first, Traffic Manager is a global service that is responsible for taking global DNS names and then mapping them to specific deployments, multiple specific deployments. You can layer policies on top of it to do nearest site, you can do load balancing, you can do health checks, you can do time-based migration. So it's effectively a global deployment router based on DNS. And what you do is you take your DNS name and you map it to a Traffic Manager name that you get when you create your Traffic Manager deployment. In this case, contoso.com is mapped to contoso.trafficmanager.net. So a recursive DNS resolver is saying whenever it sees contoso.com, it's mapping it to trafficmanager.net. Now, when trafficmanager.net gets called, Traffic Manager itself is doing a dynamic lookup, and based on the rules that are specified in your policy, we'll go and find one endpoint to return back. And so in this case, it might be some contoso/eu.cladapp.net, which then resolves to an IP address that's in EU, because that might be the closest site. And then that's returned to the client, that IP address, and now it's been routed to the EU deployment for contoso.com. And by the way, just so you're aware, it's connecting directly at that point to the EU contoso.com. It's not actually going through Traffic Manager. So Traffic Manager is only used at the time of DNS name resolution, which only happens when it's a new client talking to this for the first time, or the DNS lifetime expires and it needs to go look it up again. So on this day, where did Contoso and those other websites go when they disappeared from the web? What happened is there was a deployment that had just taken place of a new version of the Traffic Manager code. And what happens when the new deployment is deployed is that the front-end servers that are doing this processing recycle, they go down, and then they come back up and boot again and start serving traffic again. And this is a load balance system, and so it's always continuously available. There's always new programming requests coming in from our customers saying, hey, now program, here's some new rules, here's policy change, here's a new site that I want to be mapped to Traffic Manager. So we're running DNS version 81. These are real version numbers, just for authenticity. Traffic Manager at this point, this is a while ago, now it's in more regions around the world, but you can see that we had 3 regions running Traffic Manager. And each node deployment has a verification runner. So this is one of the rules that I'm not going to highlight with an incident here. I'm going to talk about best practices for runners. But how many people have something that is on the outside watching what's happening as you're doing a deployment to see if things are going well, rather than just trusting the system itself? How many people follow that? So just a few of you do. This is a golden rule. Have an objective outside observer that's watching what's going on to check the health of your service as it's being updated. Don't just trust the signals coming directly from the service. So this is what Traffic Manager has. Most of our services have this, these outside independent runners. So the verification runner is now watching what's going on as the secondaries. So you can see each one of these sites has primaries and secondaries. The secondaries are gray, and the first thing we do is update the secondaries, not the primaries. If something is going to screw up the service, we want to make sure it happens on the secondaries, not the primaries, because that's not going to impact any customers. So that's another rule, is if you've got primaries and secondaries, update your secondaries first as your early warning. So the runners are verifying after each one of these, and we're very careful with something like DNS, because this could obviously impact lots of customers. So every one of these nodes gets updated independently, sequentially, and after each update, the runners are going and verifying that things look okay. And the way they do that is they go program new rules, Traffic Manager rules, synthetically. They say, oh, I'm going to create, test contoso.com, and here's the policy Let me go verify by querying back what traffic manager thinks the policy is for traffic, and let me do DNS lookups. Yeah, everything looks good, and it does a few tests like that, and then gives a thumbs up if things are working as expected. So now we've got the secondaries all updated, the runners are all happy. Now it's time to turn to the primaries. So we start with the primaries. What happens after we update the primaries, though, is that some of those sites that were being served here end up going offline, and DNS name resolution starts failing on them. Our runner doesn't pick it up. Our runner's doing its synthetics, and things look good. So the runner says, thumbs up. We move to the next one. Do the update. Some of its programming is lost, and it starts failing DNS requests. Move to the next one. And some of its. And so Contoso.com, in my example here, is one of those sites that got deprogrammed. So what exactly happened? At this point, people from Contoso.com call us up and say, hey, what's going on? My site's gone. At that point, the live site operators go and say, we've got a deployment in progress. Looks like it's screwing up some customers. Shut it down and actually roll it back. So another rule, have rollback systems in place that automatically roll it back. So what happens is we start the node-by-node rollback. Then we start investigating what happened to make sure that the system isn't still in a messed up state. We have to root cause it immediately. So we start looking through the code, and we come across this code right here. How many people use reactive programming? How many people understand it out of those people? So this is one of those places, iObserver and iObservable, that it's hard to get it right. And what this pattern right here is that these traffic manager rules and programming are given back to the DNS programmers through iObservable. And so this iObservable starts up when it bootstraps, and that's what happened after this updated code came in, and it starts waiting for observers and giving them the set of rules that they should go program. But there's a problem with this piece of code. Now, it is this right here. Here's where the bootstrap function says, oh, I'm going to wake up, and I'm going to go emit the set of rules that I know at this point in time. And then I'm going to start to emit the rules as they get updated. As they come in, I'm going to go give the observers those updates. So when we looked at the timeline here, we saw that, in fact, it was between the time the Bootstrap server started and the time that observer subscribed to those events that everything that was programmed in that time window was lost. And it was lost because the observer didn't see the events that were being programmed at this point in time because the iObservable was only giving it the set of programming plus the initial database that it had after it bootstrapped. So this time window meant that it was dropping any new programming. And thus, Contoso.com, if they changed their rules, suddenly that was gone. So here's the actual WinDiff of that code to fix this problem. You can see that it's changed now to call observable defer. And what this does is say, I'm not going to start emitting anything. I'm going to collect stuff until I actually have an observer to give it to. And so now all those rules that are coming in, the observer finally comes up after the bootstrap, registers, and now it's going to get the full set of programming from the time that it shut down to the time it comes up and starts to ask for rules. So why did the runners miss this? Well, the runners, why did we miss this in the first place in those signals? Well, first, the secondaries aren't serving any production traffic. So they're not actually doing this kind of programming. And we only catch a problem with the runner then notices there's a runner. But the verification runners have a very short little cycle, about 5 minutes, where they're doing this programming and checking the results. And they're doing it, it turns out, after the bootstrap. And they're also deleting their entries to clean up. And so they were missing this little time window. And so thinking everything's looking good. If they'd had something persistent or they were programming during that time window, they would have caught the problem. So the root cause here is that we have an initialization issue with two pieces of the service depending on the order of each other and creating a race condition. We also, so what the rules that would come out of this, there are several rules that came out of this that we started following. One rule is to expose your secondaries, and we've learned this rule in other places too. Try to expose your secondaries and your canaries to production level traffic. So route some of the traffic there. Now you're not going to want to route all the traffic because then those secondaries can cause a big outage if you've got a problem and you're initially deploying to the secondaries. But you need to have something that's more representative of production traffic than what these runners were doing. You also need time to bake. And I'll talk more about bake time a little bit later. But another rule, and we've learned this in this case as well as other cases, when two services are coming up, whenever you have a fragile dependency of this service needs to start, then that service needs to start, you're going to end up having a problem in production at some point. You need to make your services resilient to it doesn't matter who starts up when, and we're going to coordinate as we come up so that if you start before I do, it's okay. If I start with you do, it's okay. We'll start talking to each other and we'll figure out what's going on. The state of I'm going to start up before you, unless there's a direct dependency, of course, is one where you're going to run into problems. And then minimizing initialization. One of the other rules, we had a similar situation with Link, where Link would come up and it would have a problem talking to its back-end storage system, so new Link calls, existing Link calls when it was being updated would get dropped. So what Link did is put in a cache so existing calls would be cached, so even if it came rebooted, got refreshed, recycled, came up and had trouble talking to its back-end storage system, it could continue to serve the existing calls. New calls it couldn't until the storage service was accessible again, but this is another rule to try to minimize initialization problems. So that's one example. Now let me talk about another example, and this one is a pretty recent one. How many people use Visual Studio Online? Visual Studio Team Services now it's called. It's a pretty awesome service, isn't it? Yeah? I see some people going, yeah, no. It is. I'll just tell you it is. So this incident happened in Visual Studio Team Services. Now, how many people watch or read Brian Harry's blog? So a bunch of you do. This is a blog I highly recommend reading. Brian goes deeper behind the scenes of service operation than anybody else across Azure and Azure-related services to tell you what happened, why. Whenever they have an incident, he's fully transparent and goes deep on the analysis. In this example, how many people were impacted? Anybody here impacted by this one? This was, I think, in December or January. January. This is just a couple months ago. You were? So a couple people impacted by this one. So in this case, you take a look at this. This is Monday, 9 a.m. GMT. So most of Visual Studio developers, team service developers, there's a large swath of the world where there's not a whole lot of developers using Visual Studio Team Services, but a lot in Western Europe. So typically when we have an update that's like in the middle of the night, it's 9 a.m. GMT when the service really starts to get hit. So 9 a.m. GMT on Monday morning, because this update had gone out Sunday night, things are looking cool. Error rate's low, success rate high. Developers start to come into work in Europe, and they start to use Visual Studio Team Services to do their builds. And suddenly, we see a spike in failures. And these spike in failures were to a specific service. It's a global token service. So this is part of the internal authentication systems of Visual Studio Team Services. And it's really the only remaining global service in Visual Studio Team Services. So I'll talk more with another example about a lesson. But one of the key lessons, even here, which Brian acknowledged, and they were already on their path to addressing, was try to avoid global services. Try to partition wherever you can. In this case, something happened to that global service, and now nobody was able to log in to do their Visual Studio. So alerts start to fire. VSO team starts to investigate. And as they investigate, they come across the root cause as being a particular Visual Studio Team Services stored procedure for Azure database. And this particular stored procedure call is taking so long to execute that it's causing a backup of the token services queues. to the point where suddenly authentication requests are timing out or getting delayed and causing performance to pile up way upstream. So what's going on with the stored procedure? Well, over the weekend, what they had done was update the compatibility setting for Azure Database. And the application compatibility level that they'd set was 120. So one of the things that they were doing was trying to clean up all their use of stored procedure functions to be compatible with the latest version of Azure Database and not be stuck in this old version, which they needed to get off of to take advantage of new features. So they go through this cleanup exercise over a few months. They're ready to go, flip the switch, get up to SQL Server 2014 compatibility level, and that's the way the stored procedure calls performance analysis looks. As they look at the SQL logs, it's spending all its time here waiting on a semaphore and almost no time doing any useful work. So what is going on here? Well, they take a look, and there's, in the query processor in SQL, it takes a look at the stored procedure calls query, and it performs an estimate of how much resources it's going to require. And one of the estimates it makes is how much RAM is this going to require to execute the stored procedure. When they flipped the compatibility switch, the estimate went from a few tens of megabytes to 3.5 gigabytes. Suddenly, SQL Server's query processor says, looks like the stored procedure is going to require 3.5 gigabytes of RAM. So every time it gets executed, allocate 3.5 gigabytes of RAM. The SQL Server systems are operating with like 148 gigabytes of RAM. So you can see just not many of these start to get executed, and suddenly the server's out of RAM. And now everybody's waiting for SQL to give it RAM, which is now waiting for those other stored procedure calls to get the RAM, do their processing, and then finish. And this is why you end up with this long chain of everybody sitting here waiting. Here's the stored procedure call that was the problem. And you can see that there's some query hints in here. And they had put these query hints to tell the query processor, hey, this is how you should start your query, how you should treat this particular column, where you should start seeking instead of doing a full scan, cross-join scan. So whenever you do these interloop joins, important to do these kinds of optimizations. And the query processor had looked at this and for some reason changed its mind from the 2008 compatibility version to the 2014 compatibility version to thinking this particular query was suddenly going to consume much more RAM. So and this is actually the way that the query processor looked before. So they went back and said, what did it look like before as they were root causing this? And here's the profile of that same stored procedure with the previous setting that they'd had literally 24 hours before. You can see that it's spending its time mostly doing real work, not sitting there waiting on a semaphore. And the amount of RAM, like I said, was a few tens of gigabytes. So to get this problem fixed, they put in this little hack right here, max grant %, which is basically this is an override to the query processor to say, I don't care what you think this is going to take, only pre-allocate 1% of RAM of the system for this. So this is kind of a little hack because, of course, the RAM on the system is going to vary, and 1% of a very, very large system is going to be a very, very large number, much bigger than you probably need. But this got the problem mitigated, at least, without them having to roll back to the previous compatibility setting. And now what they did is, the Azure Database engineers were on the call once this had been identified, and now they're working on, hey, how can we go change the query processor to do the right thing in this particular case? Because putting in this max grant % has, across all their other queries that might be impacted like this, and this is the first one where they saw it really being impacted in a way that was causing everybody problems, is obviously not going to scale. So they put in that max grant fix, and now you can see that the error rate goes back down to kind of a normal level, and success rates back up to normal level, and things are happy as they can now go back in the longer-term fix. Got out of the hole there. So the rules here, I mentioned this one, avoid global services as much as you can. And this is one of the nice things about, for example, Traffic Manager, the way that you can take effectively what looks like a global service, one global DNS address, and then partition it out. And this is something that we followed and we've done across our services in Azure. I'll give you another example of how we've done this, is that we had in Azure Service Manager, we've got a front end for that, for basically the infrastructure as a service v1 APIs. That thing is not partitioned across services. It's got a global deployment. It's got an active passive deployment. What we've done with IaaS v2 is go into regional deployments. And so now we have the traffic get routed to whatever region you happen to be in through Azure Resource Manager. But now there's no single global control point for the IaaS APIs. And that means when we do updates, if we do it region by region, if we have a screw up in one region, and even there we partition the service, of course, across basically update domains and try to detect problems before they impact the whole thing. But even if it gets past that, we're impacting hopefully just one region, not multiple regions, and not region pairs in the case where we've got a DR capability by letting customers fail over from one region to another. The other one is similar to the traffic manager one, is that you want to test with production traffic. And so if they'd actually had production traffic hitting Visual Studio Team Services at the point of time when they'd done that flip, they would have seen this instantly instead of having to see it in production. So if they had a canary deployment that had real type production traffic of that global token service, they would have seen this. And this is something that we've also institutionalized. For all our services across Azure, including Visual Studio Team Services, we've got a canary program now, Visual Studio is moving into it, where we've got basically canary regions, like fake Azure regions that third parties that want into this program maybe want to see if their own services are resilient, as well as our first-party services have to go in there. And now when we do rollouts, we go through there first. And the production traffic is as real as we can make it. And that way we can hopefully catch things there before they go out into real production. Also, another lesson learned here, and that we've learned this lesson in another examples, is that when you have runners or when you're watching for health signals, especially on a service like this, they had health signals going on over the weekend after they deployed. But the problem didn't show up until 9 o'clock Monday morning when developers started hitting the service at kind of production load. So one of the lessons we've learned here is that just a health signal that's based on a small time window, especially one that doesn't represent true production time, like one that's in the middle of the night, one that's on the weekend, is likely going to miss issues that are driven by production level loads. When you have a performance regression, you're likely not to see it unless you've got very sensitive health monitors looking at your CPU levels and other resource indicators. You're not going to see it until suddenly you've got all your users banging on the service, and now what was a small noise at night or over the weekend suddenly tips your service over on the edge. So we've got a rule for our services that when we go out and have it serve production traffic, that it needs to serve at least whatever the first slice is, serve at least 24 hours of production traffic during the week before we'll move on to the next slice and consider it healthy. So this is, it's kind of painful because it slows down your deployment. And you hear DevOps, agility, deploy every 10 minutes. Well, when you're dealing with services that companies are betting their businesses on, like Visual Studio Team Services, it pays to be a little more careful because one little screw up and you're causing major, major customer pain. And speaking of the noise, so one of the things that we go back and look at is how did we miss this? Because there was some ambient level of this going on even before the developers started showing up. So how do we miss that in our signals? So one of the things that we're focusing on is fine-tuning anomaly detection based on the health signals and performance signals coming out of our services. So that's the Visual Studio Team Services story. Now here's another example. This also happens to be one where people couldn't reach a website. And so imagine how our lives would be, or how your lives would be affected if you couldn't get to MSDN. It would just be a catastrophe, wouldn't it? Actually, you're probably thinking, no, not really. How about Stack Overflow? Then things would be. So here's the incident page from this one. You can see severity 1 incident, major outage of websites. So what happened here? This one has to do with the service we've got called Azure Front Door. And Azure Front Door routes traffic for all of our internal production sites. And this is what the int or staging, some people call this a staging environment, some people call it an integration environment. In this case, we call it int, but it's really staging. It's the place where we go deploy things in Azure Front Door before they end up going out into the real world, kind of the canary program. And you can see that there's a front door automation, deployment automation, with a runner, which is verifying the health of anything that goes out through to this environment. And there's two sub-environments here. There's a front door API environment. There's another front door workflow environment. So the service is built really in a multiple different environments. And then the front door nodes are responsible for, if they're part of an environment, active environment, they're responsible for doing flow requests. This is where SSL termination happens and a load balancing happens, A/B testing happens as part of front door. And then you can see there's a storage account that has a manifest container in it. And this is what defines what the environments are, where the endpoints are, where the containers, where their data happens to be in the storage account. That is all stored here. Front door has a cool one-box test, dev test experience. So the front door developers can go and test their updates on their own boxes. This one day, this developer said, you know what? I'm going to give this test a real good test. I'm going to not test with synthetic data on the manifest. I'm going to test with, by the way, there's my favorite little sticker, which anybody sends me a sysinternals bug report that I want to ignore, I just send them back this. Now, what this developer did is said they want to use the production data. And so the front door environment has a production database. It's a production environment manifest. It's endpoint, container ID, and the data that goes along with that environment. So before I talk about what happened, let me talk about the way that we do rollouts for front door. We start a new deployment. We deploy a config version n+1, for example, to the int environment. At that point, we wait for all the int environments to report back if they thought their rollout was good or not. Now, if any int sends back a negative, at that point, we're going to roll back everything back to the previous version. If everything looks good, then we move on to the primaries and wait for all the primaries to act. And if any of the primaries say something's bad, of course, we're going to roll back as well then. So this is the way that the world looks, with integration environment on the bottom. So this is kind of blowing out the diagram I had before the architecture, and the production environment in green, kind of across the top there. We've got the front door automation deployment runners. We have the production versions of the environments and the stage versions of the environments. You can see that the front door nodes over there in production, as well as the stage front door nodes. And then there's the storage account. So let's talk about what happened here. The developer is doing his development on the one box. He's got a copy of the front door production database in his one box environment. Now he pushes his update to the stage front door environment, which then ends up taking that front door database copy, which has pointers into the front door database manifest locations in the storage account with the storage account keys, and pushes that into the production manifest container. But that's OK, because this happens to really be the production manifest, the current version of it. So it's basically just overriding what was there with another copy of what was there. Now remember, what happens here is that we're going to wait for health signals. In this case, the production environment sees a change and says, oh, there's a change. I'm going to update. And it looks like there's a deployment in progress. So I'm going to go tell the production version of the environment, update looks good. Because that's what the production front door nodes do. When they see an update, they say, oh, got it. My health signals look good. Proceed. The problem here was that the int environment is the one that got the update, not the production environment. And you can see that the int front door nodes over there on the bottom right, they have no idea anything happened. And then we have this runner so that the workflow, this environment gets updated. The prod environment doesn't give back any signal. So the int environment, the runners for it are waiting for signal back from the int nodes to signal from the int environment to say that the int front door nodes have gotten the update and everything looks good. They never got anything. They never saw an update there in their manifest container. So they don't even know that they're supposed to respond with anything. So there's a timeout now. The fronter says, I didn't hear back from any of the front doors nodes. Something must be wrong with this deployment. Roll back. So what's the rollback here? It's a rollback to the last known good version of the environment manifest. The last known good version of the environment manifest for a stage is empty. So stage goes, oh, I need to roll back to last known good. Last known good, because it's the first time this particular thing was deployed, is empty, so it pushes empty to the production manifest, because that's where that manifest metadata was pointing. So now production has nothing. And so the front doors go read it, and they go, oh, that's interesting, empty manifest. No environments are active. And that would have been probably OK, because they do some extra verification that happened to have a bug in it that caused it to ignore the fact that it was empty when it should have, and then try to process it. Does anybody see a problem with this piece of code? Remember, so what's this deserialization is going to result in nothing. So give you a hint, current I filter is what? Null. So which line has the problem? Yep, line 4. There's a dereference of that null pointer. So the front door nodes dereference this and crash. One by one, they just all go down as they're processing this empty manifest data for their environments. There's my little graphic. I don't think we saw these on the servers. So this is a little made up, but just to show you, this is what happened. Dr. Watson there. So when those front door servers crash, the nodes crash, the environments go, oh, the front doors are all down, or the front door's down, withdraw their BGP routes. So now all the routes for those sites that were being served off that environment get retracted, and the internet no longer sees them. And thus, MSDN is gone. So how'd this get fixed? It actually got mitigated by itself because another developer was pushing actually a new valid deployment through prod, so that prod got updated with the current version of the manifest again. And so at that point, that got pushed to the new front door nodes. Last known good was valid, and things got back to normal. BGP announcements as the front doors came back up when they rebooted, read the manifest, things looked good, and started signaling to their environments they were good, and the BGP routes got advertised again. So traffic flowed. So the root cause here was dev was able to talk to int, or dev environment was able to communicate with int, and int was able to talk to prod. The configurations, so they were able to talk to each other, and they had their configurations mixed together. There was a storage account you saw there. That was one storage account with the manifest for both prod and int in it. And so int had the keys to that production storage account, which is what allowed that development push to stage to actually go and mess with production configuration. So rule number 1, isolate your environments. Isolate the resources they use. Don't let them share resources. Don't let them share keys. Big lesson from that. Here's another example. A little variation on what that example that I just showed you. This one's Azure Active Directory. So I've got here, authentication started to fail. This one was in December of last year. Authentication started to fail, starting with EU. You can see server area 1 resolved. We resolved the incident pretty quickly. But what happened here? Why did authentication start to fail with Azure Active Directory? To understand that, let's take a look at Azure Active Directory's architecture. So when users log into Azure Active Directory, they get redirected at a login page. Azure Active Directory invokes the authentication service, which is called Evo STS. Evo Security Token Service is the internal name. And Evo STS is actually, and Vittorio probably talked at length about this in the last session. How many people went to Vittorio's session, by the way? So quite a few of you. So Evo STS is what actually issues the tokens. And if a request is handled successfully, the user gets back their token, and now they can go on their way. So one of the things about this architecture is that there's a thread pool in there that is waiting for directory lookups to happen so that it can mint the appropriate token. And this thread pool, varies in depth depending on how many outstanding authentications there are, and it's designed to have a capacity to handle peak kinds of loads that Azure Active Directory Evo STS is going to have, looking up directory data and processing tokens. So what about a test request, or what about a request to a test tenant? One that doesn't have its directory data in the production directory, but in a test directory. What happens to that? Well, it turns out that for historical reasons, testers could go to the production front door of Azure Active Directory, and when Evo STS would see a request for a tenant that's not in the production directory, it would fall back and say, oh, must be in the test environment, and it would go and pass and try to query the directory in the test environment. There's a test DPX directory data service there that it's going to go try to talk to. What happened on this day was that DPX in the PPE stands for pre-production environment. What happened on this day is that that environment was down. It had a bug when some developer had rolled out a piece of code, and this thing was down. So what happened to Evo STS? It's got these test queries, authentications, calling out to that directory service. The directory service is down. The thread pool starts to back up. The thread pool gets to critical level, consuming all memory, and suddenly, at that point, production authentication requests start to fail. And that's why you see that can't log in. So how did we mitigate this? The quick fix was just to shut off that connection. So get Evo STS to say, if I don't recognize that, if the tenant's not in the production directory, just forget it, fail the request right away. So that was the quick fix. And we rebooted the Evo STS nodes so that their thread pools would get cleaned up and they'd forget about those failed requests that are never going to come back. I already talked a little bit about the history behind this, but we also looked at this a little more carefully and said, you know what, the production and test environment also on kind of crappy hardware. It's also going to be slower than production, and that thread pool and all the sizing, resource sizing for that is all designed for the production environment. So that's another problem that we got to deal with this test environment. Basically, the bottom line is we should not be having production talk to test environments at all, even for this kind of path that we thought was innocuous, because look at that test environment had a direct impact on production. So this is kind of an inverse of the other situation. Production and test not being mingled in terms of their configuration, but even being able to talk to each other was a problem. So one of our lessons learned here is do not allow production to have any dependency on test, because test is just a wild, woolly kind of environment. You don't know how it's going to behave, and you don't want to run the risk that something screwed up there that production developer, the code is designed for production kind of assumptions is going to be impacted by your test environment. We also want to have graceful degradation. So what should happen is, and many of our services do this, is load shed. Right? You start not failing, the thread pool starts to back up, you start to shed load, drop requests so that you don't start to just completely keel over, but you run in a degraded mode instead. Well, at least some production traffic would have gotten through, rather than it all starting to fail at the same time and being basically a global outage. And then finally, I've got one last one to leave you with. Here's a real-life incident. This is a screenshot of an incident. It's hard to read what the incident was down there, so let me blow that up for you. So avoid, having doing some s'mores in your data center. This is the lesson for this one. Yeah, so that's really how often do you see that in an incident report? All right, so here's a summary. We're about out of time. Here's just a summary set of the rules that I've shared with you from using kind of the standard modern cloud best practices we started with. Code hygiene still matters, log well, handle your exceptions well, log in UTC, keep your secrets out of your code, beware of race conditions on startup. Configuration, one of the things I want to emphasize configuration equals code. You know, you hear that statement? What that really means is you should never, basically when you turn on a feature flag, treat that as code. Treat that as a code change when it comes to the safety of that thing and validating it as it goes through your normal pipelines and not just saying, I'm going to blast a configuration update out to the world. Keep your prod and dev and stage environments completely isolated, and then finally try to ensure graceful degradation. There's one other talk I want to point you at, and this is the CAT talk in the CAT clinic. So Mark Souza is giving a talk Friday, 2 p.m., on architectural best practices. So I kind of gave you the rules of the road here, but he's going to give you architectural guidance, and then you can go to the clinic. And finally, fill out your evals, use this knowledge for good, and if you come up here and stand in line, I've got a bunch of these stickers to hand out to whoever gets up here first. It's what I've got on the back of my laptop, and so it's all the cool kids have this sticker. So with that, I want to thank you very much, and have a great build.